Good evening, everyone. My name is Douglas Sprang, and I lead the Energy Environment Series for the MIT Club of Northern California. Boy, I don't know about you, but that music at the beginning, I hope you were here for the whole thing. That was brought to you by our club admin, Serena Chung. Thank you, Serena. It moved me. I'm all choked up. I don't know if I can do this intro, but at any rate, what a great way to start the new year and our new event for the 2024. So I'm delighted to kick off our first event of the new year. Over the years, we featured top speakers in the fields of renewable energy, electric vehicles, storage systems, hydrogen, and climate change. Tonight, we'll present a new twist on climate change, featuring two MIT alums who have conducted a significant amount of research on how to take a more holistic view of dealing with it. Our primary speaker this evening is Arizona State University Professor Bhavik Bakshi. His presentation is entitled Choosing the Best Technologies to Combat Climate Change, which will go well beyond a discussion of just energy technologies. He will be introduced by his longtime collaborator at Ohio State University, Joseph Fixel, who will provide an overview of the concepts behind what Professor Bakshi will present. We have enabled live Q&A, and I'll do my best to get some of these questions to our moderator to add to the many questions we got from online registration. But we won't be able to get to all of them due to tonight's large audience. So it's time for our program to begin. I'll be back at the end of, oh wait, I forgot to say, by the way, we recommend for your best viewing experience to put your Zoom view in gallery mode. Okay, now it's time for our program to begin. I'll be back at the end to close things out, but now I would like to introduce our moderator, Joseph Fixel, who will orchestrate tonight's fireside chat. So take it away, Joseph.
Thank you very much, Douglas. We've been planning this for several months, and I'm really excited about this. As Douglas mentioned, my collaborator is Bhavik Bakshi. Bhavik, can you put up the slides, please? Bhavik's going to share his screen. And as Douglas mentioned, I have collaborated with Bhavik for many years. We were both at Ohio State for some period of time. He is a brilliant scholar. I'll tell you more about him later. Myself, I spent a lot of my earlier career in private sector, and I did a lot of work at Battelle on sustainability. That's how I first met Bhavik. We were both in Columbus, Ohio at that time. I'm now retired, and I do a few things on the side. One of the things I love to do is to organize webinars like this to talk about the frontiers of climate change. Let's go to the next slide, please. So let me start by just showing you the sort of traditional view of sustainability, which is basically companies support communities, communities provide human resources, they have good jobs, they invest in companies. So it's kind of a happy marriage. You could call it a positive value flow, reciprocal value flow. What's missing from this picture? Well, obviously, it's the environment. Fact is, traditional economics pretty much ignored the environment. It was considered as an externality. It was not really factored into financial decision-making. Next slide, please. And what we've done over the years at Ohio State and working with many collaborators around the country, including the US EPA, we developed a model which we call triple value. And it shows the flow of value from the environment into both industry and society. We benefit from the environment in many different ways. Bhavik will go into this more, but I want to point out something, the idea of circularity. You can see that there's a lot of waste that emerges from both industrial activities and communities. And traditionally, that has just been jettisoned into the environment, and it has degraded the environment. What we've discovered now is we can recover materials, we can recover energy, we can convert waste into value. And that's the idea of circular economy. Bhavik will discuss that quite a bit more. But what we're going to do today is talk about a systems approach. Systems approach considers economy, society, and environment as interconnected systems. And the question is, can we model these systems? Can we measure the value that's created? Can we make decisions based on environmental value as well as financial value? Next, please. Now, all of that, what I just described is all about creating a sustainable world, but there's fly in the ointment here. It's more than a fly. There's a major issue we need to deal with, which is turbulence. We live in a world that's in constant flux. And the fact is that sustainability is not a static condition. There are a lot of dynamic activities going on. Now, I'm not going to talk about the details of this slide. Obviously, it's very complex. This comes from the World Economic Forum. Every year they meet at Davos to discuss the Global Risks Report. And it used to be that they tried to measure the global risks. So they would talk about, what's the probability of a hurricane or whatever, adversely affecting supply chains in North America, things like that. But then they started to realize that all these risks are interconnected, that environmental risks such as climate can influence geopolitical risks, societal risks, and that technological risks also can create disruptions. So we live in a highly connected, networked world that's very turbulent. So that model that I showed you is somewhat simplified, and we have to look at the dynamics as well. Next slide, please. And so we use the term resilience to describe our ability to survive in a turbulent world. Not only to survive, but to adapt and flourish. And it turns out that resilience and sustainability are interconnected. Sustainability is really a long-term concept. It's about living in harmony with the environment and making sure that we protect natural resources that are essential to our well-being. Resilience, on the other hand, is more of a short-term issue. It's how do we deal with disruptive forces that may be unexpected. For example, a pandemic, a violent storm that brings down entire cities or critical industries. So all these things need to be considered, and we need to be prepared. We can't necessarily predict when they'll happen or if they'll happen, but we need to have the capacity in terms of, it could be just redundant resources, or it could be flexibility, some sort of adaptability to be able to handle those kind of crises. Now, we're going to talk about energy technologies, and I just want to make a final point. It's important to realize that sustainability and resilience are interconnected, and I showed you in the previous slide, they can be mutually supportive, but they're also trade-offs. They're mutually supportive here. So, a sustainable society is more resilient, and a resilient society is more sustainable. But go to the next slide, please. But there are trade-offs as well. So, for example, in developing countries, people use a lot of diesel backup. That provides resilience in the case of power failures. And in places like India, where I've traveled extensively, it's essential to have diesel backup because power failures happen frequently. However, that's not a sustainable technology. It's going to create carbon emissions, and it's costly, and utilizes energy inefficiently. On the other hand, if you think about nuclear energy, well, that arguably is more sustainable in the sense that it has virtually zero carbon emissions in operation anyway. However, there are concerns about the resilience of nuclear plants, and I won't go into it, but there are a lot of proponents of nuclear power, but there's also a lot of fear about the vulnerability and the fragility of those kind of operations. Corn ethanol is both less resilient and less sustainable than other technologies. It's a no-brainer, really, that you hardly get a little more. You get a little more energy back from corn ethanol, but it takes almost as much energy to produce a gallon of corn ethanol as you get from actually burning it. Finally, you think about smart grid. Now, a lot of utilities are excited about smart grid because it'll allow them to operate their networks more efficiently. But smart grid also holds the promise of accommodating renewable technologies, distributed power, so that you can have neighborhood grids and actually decouple from the central grid if there is a power failure. So it's very useful to think about the synergies and the trade-offs in terms of sustainability and resilience. And of course, we cannot forget the financial implications. What does it cost to introduce new technologies? And what are the trade-offs? It's a complex problem. Luckily, we have a scholar with us today, Bhavik Bakshi, who's spent a good part of his career trying to unravel these challenges. And he's done breakthrough work on quantifying and analyzing these sort of systemic issues that I've described. So next slide, please. You can look at Bhavik's bio. I'm not going to go into all his honors and awards. He's really a distinguished person in this field. He's a great collaborator. He's also highly interdisciplinary. He's worked with economists, ecologists, and all kinds of different scientists, including social scientists. Now, recently, Bhavik was recruited to Arizona State. He accepted an endowed chair there. So it's been an exciting time for him. Over the last year or so, he's completed this transition, bringing a lot of his students with him as well, his graduate students. And Arizona State, you may know, is a leader in sustainability and resilience. And they have a very integrated approach. They have, the different schools work together. They're not like silos. They actively try to collaborate. So I congratulate him on this move, and I think you'll enjoy his talk. So without further ado, let me introduce Bhavik Bakshi. Please turn on your camera and your sound, Bhavik. Thank you.
All right. Thank you very much, Joseph, for that very kind introduction. And thank you, Douglas, for organizing this event. And thank you to all of you. It's wonderful to meet you virtually, in quotes. And hopefully, our paths will cross maybe at MIT or some other related activities. So what I want to do is, talk about some of the work that we have been doing for the last many years, focusing on this question, of what should we do about climate change? How do we combat climate change, and how do we figure out what are the best sort of alternatives or technologies, to utilize for combating this challenge that all of us face in the world today. So the three goals that have been, very popular these days among people in industry, among nations, and even among university campuses are to get to net zero, to make nature positive decisions, and to make people positive decisions. So the motivation for these goals, is basically these interconnected crises that are facing the world, and Joseph described several of them in his introduction. So if we want to address those kinds of interconnected crises, economic issues, biodiversity loss, climate change, geopolitical challenges, etc., it seems like what we need are efforts that address these three goals. So net zero is a goal that many of you may be most familiar with. It is probably the one that is best known among these three. So the goal here is to get, is basically to try and get our emissions to net zero. Net zero means that you're looking at the entire life cycle, and I will explain that in a little bit more detail, later on. So the focus usually tends to be on getting to net zero emissions of greenhouse gas emissions, but it doesn't have to be just greenhouse gases. This kind of a goal very much applies to any type of pollution, and such goals, as I will describe later on, have also been set forth for items like plastics escaping into the environment. The second goal is that of nature positive, and this goal aims to address ecological degradation by reversing loss of biodiversity and restoration so that ecosystems can provide the goods and services that all of us depend on. People positive is a goal that is oriented toward addressing, social inequities. Equity and justice kinds of issues are the ones that come into the picture over there. In today's presentation, I'm going to focus primarily on the first two goals, net zero and nature positive, There is work that we are doing in people positive, but it did not make sense to try and squeeze everything into one presentation. So the big challenge in meeting all of these goals is that there are a lot of possible solutions, and solutions have their trade-offs, pros and cons. So the challenge is to figure out how to manage those trade-offs while avoiding unintended harm. So net zero, as I told you, has been the most popular, and there have been a lot of corporate and national pledges toward getting to net zero. So this slide shows some of the headlines from various news sites, about lots of companies. Almost all the large companies, for sure, across the world have pledged to become net zero by as early as 2035, and roughly many of them by 2050. So here is a little blurb from Dow Chemicals goals. So what they have said is to protect the climate. So by 2030, Dow will reduce its annual carbon emissions by 5 million metric tons, which is a 15% reduction. And by 2050, Dow intends to be carbon neutral. So they're going to look at scope 1, scope 2, and scope 3 emissions. So scope 1 are the direct emissions from their processes. Scope 2 are the emissions that come from electricity and other energy use. And scope 3 are the rest of the life cycle, including all the upstream processes and all the downstream activities associated with their products. So this is obviously, very encouraging, but at the same time, there is a fair amount of skepticism and doubt as to whether these kinds of pledges are actually going to be met. Another pledge that is also very common is related to plastics. As you may know, plastics pollution is a huge problem. There's a lot of microplastics in pretty much everything, the air we breathe, maybe even the water we drink, but surely in the oceans, and you go to any beach anywhere on the planet, you will see plastic waste on them right now. So this corporate environmental pledge about plastics is to get rid of, is to identify the problematic plastics by 2025. And also, get 100% of plastic packaging by 2025 to be reusable, recyclable, and compostable. Also 50% of the plastic should be, either recycled or composted by 2025, and 30%, there should be recycled content, or the plastic should be bio-based. These are very ambitious goals, and they're reflected in the pledges of many companies, especially ones that make plastics. And here is another blurb again from Dow Chemicals goals, where they are talking about transforming plastic waste into other forms of alternative feedstock and commercialize 3 million metric tons of circular and renewable solutions annually. Again, very commendable goal and a lofty goal. But there is skepticism and doubt about these goals also. 2025 is not very far. It's basically next year. And it doesn't seem like these pledges are actually going to get met. So, the goals are great. Getting there is, needless to say, not easy. And we don't want to get there and break the bank. We need to get there in a manner that is sustainable, both from economic, environmental, and societal points of view. So let me now talk briefly about this nature positive goal. So the nature positive goal is coming, from the level of the United Nations. It's been talked about at Davos, at the World Economic Forum, their meetings. A lot of companies are also now pledging to become nature positive. And the idea there is that if you look at this graph here, biodiversity on the y-axis and time, as you can see, on the x-axis, and biodiversity over the last many, many decades has been declining. So the goal about nature positive is that by 2020, there should be zero net loss of nature. And by 2030, human activity should be such that it results in restoration of ecosystems and reestablishment of biodiversity. If business as usual continues, then we have this gray line, this gray curve, where biodiversity would continue to decline, and that would be far from sustainable. The idea behind nature positive is to have full recovery of biodiversity by 2050. Again, very lofty goal, and I'm not sure if we are really making progress in, to meet these kinds of aggressive targets. However, the World Economic Forum has estimated that if by 2030, businesses that focus on these nature positive and people positive types of goals they are expected to have $10 trillion of business opportunities from, trying to move in these directions. And the potential is that they would create 395 million jobs. So the potential is huge, if these goals are pursued and met. So the opportunities and challenges enabling this transition to a net zero future and a nature positive future, there are a lot of opportunities, but also a lot of formidable challenges. The opportunities are that we have the potential, and by we, I mean, it could be, we can think of ourselves individually, but maybe more importantly at a corporate level or at the level of a country or a society. There is the potential to simultaneously capture market share, enhance competitiveness, improve environmental quality, and meet societal needs all together. This is, it seems to me, a rare opportunity. Surely in my lifetime, I don't think such an opportunity so far has appeared. The challenges are very substantial, very formidable, because there are these trade-offs between economic, environmental, and social aspects that we don't even necessarily fully understand, but we need to, make sure that we manage these trade-offs in an effective manner. The other problem is that, these kinds of, in any decision, where that if you consider a narrow boundary and you think you have solved the problem within that narrow system boundary, oftentimes what has been shown historically is that you don't end up solving the problem, you just shift it outside the boundary. So this burden shifting is a major challenge, and this shifting can happen across space, across time, across different impact categories, like you may save energy, but you may need a lot more water, and across disciplines. You may find an engineering solution to a problem, but the problem may reappear as a human behavioral type of a problem. So that burden shifting is a substantial challenge. Of course, we need alternatives. We need technologies, we need innovation in technologies, but technologies alone are not going to be enough. We also need policies, and we also need changes in human and societal behavior. In addition, this whole system is complex. There are, extremely difficult, often nonlinear dynamics in there, and there are a lot of things that are unknown, what is often referred to as deep uncertainties. So, one of the reasons for moving to Arizona State University is that we are in the process of establishing a center, and I'll tell you more about that, at the end. But the research objectives of the research that I've been doing for some time and the center that we are in the process of establishing is to develop systematic methods, models, and tools. By tools, I mean software tools, to guide the transition to a net zero, nature positive, and people positive future. We want to develop, being in academia, obviously we want to develop these methods and tools in a manner that is theoretically rigorous. But at the same time, we want to do this in a manner that is practically relevant. So we want this research to be use-inspired and guided by the stakeholders, corporations, nonprofits, government, etc. Our current emphasis is on the chemicals and materials industries. However, the methods we are developing are going to be very general, and they would be applicable, to other industries, but also to nations and other, places like that. So before I get into showing you some of the work that we have been doing, what I want to do is just, make sure that this idea of the need for a systems approach is very clear. Joseph did allude to that in his introduction, so I'm going to kind of revisit it, maybe from a slightly different point of view, because this is a fundamental requirement of any research or any activities, any efforts toward meeting these goals like net zero, nature positive, etc. So let me give a very simple example. Okay, so in this figure here, this bar plot, what I've shown is the carbon footprint of different technologies for generating electricity. By carbon footprint, what do we mean? Basically, is the total emissions of greenhouse gases in the entire life cycle of that technology or of that activity. By life cycle, we mean all the way from the cradle, so to say, extraction of resources, manufacturing, transportation, making the product, using the product, disposing the product, and it may go into the environment, or it may get circularized, it may get recycled, etc. So that entire life cycle is what we want to look at. So the total greenhouse gas emissions in the life cycle is what is referred to as the carbon footprint. So in this slide, you can see, if you look at the fossil resources, hard coal, lignite, natural gas, and oil, they have a pretty high carbon footprint as compared to these other resources. Many of them are renewable. So you see biomass, hydropower, solar, and wind being the renewable resources. They have a much smaller carbon footprint as compared to the fossil resources. Nuclear also has a very small carbon footprint. So, if our intention, our interest is in getting to net zero greenhouse gas emissions, it makes sense to utilize these renewable energy technologies, which is what has been happening. I just had solar panels installed on my roof. I'm in Arizona, so lots of sunshine, and they were activated only day before yesterday. So, from a net zero greenhouse gas emissions point of view, that does make a lot of sense. But notice that no technology is without emissions. Nothing is net zero. Okay, everything has some non-zero emissions of greenhouse gases, no matter how small. The other very important thing to realize is that, yes, renewable resources do have a smaller carbon footprint, but they do have a larger impact in other categories, such as land use. For example, if you consider hydropower, which has a very low carbon footprint, hydropower, takes up a lot of land. Due to the dams that are built and the rivers that are controlled and the lakes that are created. It also can result in a loss of biodiversity because of the forests that oftentimes get submerged. If you look at, renewable technologies, other renewable technologies like solar and wind, and the associated batteries, etc., that we need, those technologies are less carbon intensive, but they are more materials intensive. We need all these minerals that go into these technologies for making, the solar panels, for making the wind turbine blades, for the batteries, etc. Of course, in many cases, we need a lot of water. And there is the issue of societal preference. There is opposition to some of these renewable and low carbon technologies. Nuclear is one example that is very well known. Joseph also mentioned that at the beginning. So we need to take a systems view, because if we only focus on reducing greenhouse gas emissions, we may address the climate change problem, but we will end up with other problems, such as the challenge of losing biodiversity. Also problems associated with the use of materials and the environmental impact that those activities, especially mining and so on, are likely to have. So we need a systems approach to make sure that we solve the full problem and don't just shift the problem outside of the carbon dioxide and the greenhouse gas emissions impact category to biodiversity loss and land use change in materials use and water use types of categories. So systems approach is critical to prevent burden shifting and selecting the so-called best technologies. Best is in quotes because, as you will see, nothing is going to be perfect. Everything is going to have trade-offs, and there is going to have to be some degree of subjectiveness, in the decision making. Okay, so let me now move to an example that I'm going to use. This is an example that I'm going to use, for the next several slides. It's a very simple example, a decision that most of us, if not all of us, have made at some point or the other, which is selection of a grocery bag. Okay, so as you know, grocery bags can be made from different materials. You can have the standard, single-use kind of a grocery bag, which is shown on the left in blue, which is a polyethylene bag. There could be a paper bag. There could be cloth bag. There could be bags made from polylactic acid, PLA, which is a biodegradable polymer, and several other options. So what we want to do is we want to now address this question. How do we identify, how do we select the best technologies for making grocery bags net zero? Okay, so grocery bags have a carbon footprint. We want to get rid of that carbon footprint. We want to have grocery bags that have no emissions. So how do we do that? Okay, so this is the partial life cycle of grocery bags. Okay, what you see on this slide. So you see over here, I have HDPE, LDPE, those are high density polyethylene, low density polyethylene, polypropylene, polylactic acid, and paper. All right. So these bags get used by households. The household may reuse them. They may litter them. These dashed blue lines are littering that's entering into the environment, or they may dispose them off properly and they go to an MRF or a materials recovery facility. And from the materials recovery facility, the bags may end up in a landfill, or they may undergo pyrolysis, and you may recover some materials and energy, from it, and that energy may get used to drive other processes in the economy. They could be incinerated. The bags could be segregated, and the compostable ones like polylactic acid and paper could be composted. They could go into making plastic lumber or cement clinker, or they could be recycled, maybe chemically or mechanically, and go back into the manufacturing process. If it is done mechanically, then many times these bags end up being downcycled. So they may not end up in the form of a bag. They may end up in the form of some other less valuable product. Or they could be chemically recycled, in which case you can basically keep the material in the system and establish a truly circular economy. So if you think about every step in this diagram, there are many alternatives, right? Just the MRF, after the MRF, there are all these alternatives: landfilling, pyrolysis, incineration, etc. Recycling, there are multiple alternatives. The manufacturing process, there are lots of alternatives. If you look at the upstream life cycle, we could use many different types of energy resources, for that. The behavior of households is going to be different. So even this very simple case has a large number of alternatives, and each combination of alternatives, each pathway has a different circularity, a different life cycle impact, and a different cost. Okay. The question we want to answer is, which is the best pathway? Is that pathway going to give us net zero emissions? If it does not give us net zero emissions, how do we innovate to get to net zero emissions? So here are, I'm going to skip the methods behind this. That's all published work. There's a lot of optimization and other modeling that goes behind this. I'm directly going to go to the solutions that we have found. Okay, because I think those are interesting, and I'm going to spend a little bit of time on showing you a variety of scenarios. So here is one solution that we have found with currently available technologies. These are the technologies that are already present today. These are the recycling methods that are currently available. These are the waste segregation methods that are currently available. These are the manufacturing methods, and the power generation technologies that are currently available. On the y-axis, I'm plotting circularity. Let me tell you briefly how we are defining circularity. Circularity, the way we are defining it, it is basically the ratio of the value, the monetary value that we recover by recycling our product divided by the total value of the product. Okay, so if by recycling we can recover the full value of the product, we will have a circularity of 1 or 100%. Okay, which is over here. You see, this is 1 right here. I hope you can see my cursor. It is possible that many times the recycled material will be less valuable than the original product. In that case, you will have a circularity index of less than 1. Okay, but it is also possible that if you upcycle your product, you may make a more valuable product from the original material that you're recycling. And in that case, your circularity index may even be more than 1. In that case, you're upcycling. All right, so with the current technologies, the types of solutions that we get are shown by these circles. And you can see the circles have a different color and different sizes. Basically, the color, the brown color and the small circle, the size and the color kind of mean the same thing. The smaller circle indicates less cost. The bigger circle indicates more cost for making making the bags. The x-axis has the carbon footprint. All right. So if we want the cheapest bag, that is the smallest circle over here. Okay. It has a non-zero carbon footprint. Actually, it has a pretty decent carbon footprint. Notice the circularity index is 0. What that is telling us that the best way of using a conventional plastic bag is to litter. Don't recycle, don't bother recovering it. Now that may sound very strange, right? What I'm telling you is the best way of using the plastic bag is to literally at the end of, once you're done using it, open your window and throw it out. Okay. The reason that is a solution is because recycling costs money. If you want the cheapest solution, okay, from a traditional monetary point of view, that is the kind of solution, that makes the most sense. You don't have to put in any effort. No recycling trucks have to come by and pick up the bag, from your house, or you go to the grocery store and put it in that bin, etc. None of that is needed. Obviously, that's not the right solution. It's not the desirable solution. So you want more circularity, which is what the Global Plastics Pact, expects people, companies, societies to do. As you increase circularity, notice as you go from nearly zero circularity, increase it, the cost increases, and you want to go to more circularity, you can't really increase the circularity too much with the current technologies. And even for a tiny increase in circularity, you end up with a large increase in the carbon footprint. Okay, so these blue circles over here have a very high carbon footprint, and they are also more expensive, and the benefit, improvement in circularity is very small. So with the current technologies, we certainly cannot get net zero emissions. By the way, this red line here, the dashed line, is the line of net zero emissions of greenhouse gases. So any technology that has net zero emissions should be on the line. Anything to the right of the line have net positive emissions. Left of the line will be net negative emissions. So we cannot get net zero emissions with the currently available technologies for grocery bags. We can also not be very circular, so we cannot get net zero emissions of plastics either. If you want to increase circularity, it's going to cost you more, and there is going to be a high environmental impact. By the way, the bottom, these bars over here at the bottom just show the current combination or one of the combinations of fuels of the energy mix and of the materials. These are basically fossil-based plastics that we end up making in this case. This is currently available technology, all right? Obviously, it's not adequate. So many times people say, we want to get to net zero, so let's use renewable energy. Of course, let's use renewable energy. As I showed you earlier, renewable energy has a much smaller carbon footprint. So here is what we get if we use renewable energy in making our plastic bags, okay? So, basically we get closer to net zero. These are the points that are closer to net zero as compared to the conventional plastic bags. For conventional plastic bags, we were at about 2.5. Now we are at about 0.5, which is great from a greenhouse gas point of view. But notice circularity is still close to zero. If you want more circularity, you can have more circularity, but you end up emitting more carbon dioxide. And you want to increase circularity, not really possible. Just like in the previous case, you end up with very expensive solutions and they have a larger carbon footprint. So with renewable energy, we can reduce greenhouse gas emissions, but we cannot go to net zero emissions. And the reason for this is that industrial heating is not electric yet. We cannot use renewable energy for industrial heating, not yet at least. Circularity also tends to be very low in this case. If you want to increase circularity, it costs you more and the carbon footprint increases. So just using renewable energy is not going to be enough as far as these grocery bags example is concerned. Okay. Also keep in mind, as I said earlier, renewable energy is more materials intensive and it can have a negative impact on land use, biodiversity loss, and waste generation. So notice over here that this is one of the scenarios represented by the dots in this diagram. We are using solar energy in this case, but our resources are still mainly fossil-based resources for the plastics that we are making. So you may be thinking, but there is all this research going on, right? There's all this research going on, and all these companies have come up with these chemical recycling methods for plastics and so on. All right, let's consider those. So now we are including renewable energy plus the emerging, what we are calling eco-innovations. And now things start looking more promising. Notice, first of all, this red line, we have alternatives that are on the red line and to the left of the red line. So it is possible now for the grocery bags to go to net zero, in fact, go even to net negative. However, it's going to cost you more. Okay. Now, yes, with increasing experience and so on, it is likely that the costs will go down. This is the best estimates that we have right now of the cost of these emerging technologies. These are estimates at this point. Okay. We are, trying to look into the future, obviously. So it is possible now with with emerging technologies in the future to achieve net zero emissions, it is also possible, notice, to have a high degree of circularity. Notice circularity goes up to 75%, right? Because, as I will show you on the next slide, there are chemical recycling methods that are being developed that are actually upcycling. They are making materials from these plastics that are more valuable than the grocery bags themselves. So, the energy mix is you see, renewable. The materials that we use are also bio-based now. Okay, polylactic acid is usually a bio-based product. It's a bio-based plastic, and we're also making polyethylene coming from biomass. It could be from sugarcane to ethanol, ethanol to ethylene, ethylene to polyethylene. So with advances in technology, it is possible to get to net zero greenhouse gas emissions for grocery bags and get to a high enough circularity. So the big question then, I think this is good news, right? So there is, the importance of technology becomes very clear over here. Now this is not possible today. These technologies are being developed right now, okay? And it's going to take time for the technologies to develop and for them to become ready for adoption in the marketplace. Companies and nations have goals of becoming net zero by 2040, 2050, and so on. So what we need is, what are the actions that we should take? Okay, say a company or a nation, which technologies should it focus on in terms of investing money? Or maybe a corporation wants to buy a company that is developing these new technologies. Well, which one should it focus on? So, we have addressed that problem also, essentially by, developing methods that can provide a roadmap for how do we get, for the grocery bags example, from where we are today to net zero, say by 2050. So let me show you those results on the next slide. So, there is a lot of, again, optimization stuff going on behind this. I'm skipping all of those details, but again, sticking only with a simple grocery bags example, what we find is that you see the x-axis here is the year. So 2020 is when we did the study. At least that's the data that we used. And we are going up to 2050, 2055, okay? And what this plot is showing is the fraction of the different technologies that we would use over time. So the blue is the current technology. I already showed you the results for the current technology. That's mainly fossil-based resources, mainly, the conventional kinds of plastics. According to the models that we have developed of the evolution of emerging technologies, pyrolysis of low-density polyethylene is likely to become available by approximately 2025, and that will get adopted, okay, and will start getting used extensively. But then over time, linear alkyl aromatics from polyethylene is also going to become available. This is a technology that is still at a very early stage, but it looks extremely promising. So that is one that we expect is going to become available. By we, it's not just us doing the work. There's a lot of input coming from, from many players, including industry, in terms of coming up with these technology evolution estimates. Eventually, polylactic acid, which is the biodegradable polymer, that is likely to replace everything, or that is not replace everything, but is also going to come into the picture, primarily because alkaline hydrolysis methods that can allow recycling of polylactic acid, chemical recycling of the polylactic acid will become feasible. This plot over here shows the emission profile over the same time period. So you see the colors being the same thing as on the left-hand side plot. And you can see that the emissions, which are currently at 8,000 million kilograms of, or 8 billion kilograms of carbon dioxide equivalents, per year, will go down, as we adopt these other technologies. And eventually by 2050, we can get to net zero emissions. From the circularity point of view, circularity right now is very small, but with new technologies, we can increase the circularity. The linear alkyl aromatics from polyethylene, this alternative is an upcycling method. So that really helps in getting a circularity all the way to 1 and even above 1. Okay, so it is possible with these technologies, if they develop over time in the way we have estimated, to meet the goals of net zero greenhouse gas emissions and a circular economy for these grocery bags. Okay, so the intention behind showing you these grocery bags example is to give you an idea of what is possible and the type of methods and models and so on that are being developed and to some extent have already been developed. But now you may be thinking, come on, grocery bags, that is such a simple problem, right? We need the entire industry to go to net zero. We need, the entire nation to go to net zero. And, why do we, how are we going to deal with that problem? Obviously, that problem is a lot harder. And I completely agree with you. So what we're working on now is focusing on the chemicals and materials industry, okay? And the first thing we need for doing this type of work to apply the methods that we have been developing is we need a model of the chemicals industry, which is something that has not yet been available in the public domain. So the first thing we have done over the last few years is to develop this model, which is now almost ready, and we're going to, we are in the process of writing a manuscript on that, and we're going to make this model available to everyone for non-commercial use. The idea being to jumpstart research of this type. Without such models, it is very difficult to identify what are the best pathways and what will be the role of innovation, etc. So this figure here is showing you about 1/4 of the model, because the whole model is really complicated. This is also a mess, as you can see. And this is only showing the carbon flows in various chemicals. And the blue indicates the carbon that is there in the materials that we use in society that go into the economy. And the orange is indicating the carbon that is eventually ending up in the environment, mostly as carbon dioxide. Okay, so this is just to give you an idea of the type of model that is being developed, and we are working. The goal of this center that I've mentioned is to essentially focus on developing roadmaps and strategies for getting to net zero for the entire chemical industry. We could focus on individual products like the plastics that I mentioned previously. We could focus on a collection of products that may represent a corporation's activities, or we could consider an entire nation or the world for that matter and come up with strategies at multiple scales. Okay, so let me stop now with the net zero part, and the next 10 minutes or so, I want to talk about this goal of nature positive. Okay, because remember in the introduction, I talked about net zero, nature positive, and people positive. People positive, I'm not going to talk about today, but let's spend a little bit of time talking about nature positive. And for that, what I want to do is introduce, the importance of ecosystems to engineering. So as you may know already, industry depends on nature. Without ecosystems, industry or any human activity cannot be sustained. From the industry point of view, nature is the source of various goods like water, minerals, biomass, and so on, which is also shown in this little cartoon down here. The emissions that come out from a manufacturing process like carbon dioxide obviously can be taken up, by trees and soil, etc. But trees can also take up other air pollutants like sulfur and nitrogen oxides and particulate matter and so on. Nature can also provide other co-benefits like, recreational facilities. It can provide flood regulation, and it can provide food, and it has a lot of aesthetic and spiritual value as well. So what we've been, if you think about nature and engineering, traditionally engineering has ignored nature. And why just engineering? As Joseph also mentioned at the beginning, virtually every discipline, economics, engineering, every discipline except ecology has ignored ecosystems, okay, for the last 200 to 300 years, all right? So what we've been working on is this idea that we should not ignore nature if we want sustainability, but let us explicitly account for the role of ecological systems and see if we can come up with designs, of technological and ecological systems that are mutually beneficial, that are synergistic. So the idea is this framework that we have been calling techno-ecological synergy that we have been developing over roughly 10 years now. And let me show you, what is possible with, developing these kinds of synergies with ecological systems. So what I'm going to do is show you one example and then quickly mention a few others that we have done. So, given my chemical engineering background, my examples are chemical industry oriented, but the results, I think are much more broadly applicable, other industries as well. So in this example, we are considering a chlor-alkali process. We are making chlorine, and this is a process that is in Galveston, Texas, okay, which does have these kinds of processes, So, and the goal is that ground level ozone is something that we want to manage, we don't want that to increase too much. And, this is an electrolytic process. So we have a coal burning power plant that is generating electricity that goes into this electrolytic cell. and the nitrogen oxides coming from this coal burning power plant go into a traditional technological system, a selective catalytic reduction unit, which is very much like a catalytic converter, in the end of a internal combustion engine car. So the NO2 can be treated over there and then released. Alternatively, trees have the ability to clean the air. So we are considering the scenario where we, restore ecosystems in the region surrounding around this manufacturing process. And there is land available. We have looked at the GIS maps, etc. There is land available, and it is possible to restore the original, the indigenous sort of ecosystems that used to exist over there. So, we use this model from the US Forest Service called iTree for figuring out the role of the trees. And we also look at the impact on society using this model called BenMap, which is from the US EPA. We account for the cost to the company of all of these activities, and we also account for the cost to society from these activities. Cost to society includes the health impact of these NOx emissions, right? Because these NOx can, it's a pollutant, right? It can result in ground level ozone formation and respiratory challenges, etc. So that is also being included, in our calculations. So here are the kinds of results we get. On the x-axis is the cost to the company. This is the cost of production. Obviously, from the company point of view, smaller the cost, the better. And here is the cost to society. This is mainly the health impact of the pollution. Obviously, from the societal point of view, the cost is smaller, the better. And here is zero in terms of, societal cost. So if we were to use only technology, only the selective catalytic reduction unit for, treating these NOx emissions, then this is the trade-off curve or the Pareto curve that we find, this orange colored curve. So point A is the lowest cost solution, okay, from the company point of view, but to society, it has the largest impact. If you want to reduce the impact on society, you can use more technology, okay, put more selective catalytic reduction units. Obviously, it's going to cost you more money, so the cost to the company goes up. The cost to society can go down to zero, but it cannot go, it's very difficult for it to go to below zero. Even getting to zero is very expensive. So this type of traditional manufacturing is usually, it has a negative impact. Good for the company, but it can be bad for society. That's a win-lose kind of a situation. If we were to establish synergies with ecological systems, here is the curve that we get, the green one. Look at point B over here. This is the lowest cost to the company, okay? And this cost to the company, is less than the cost with only technology. Trees cost less money, okay, to operate as compared to technological equipment. Yes, trees take time to grow. They do need land. But once they are there, once they're established, they don't depreciate. They appreciate over time. And they don't need a lot of management. Okay? So point D is a solution that is win-win. Though lower cost to the company, and notice lower cost to society as compared to point A. With more trees, you can actually go to zero impact on society with a little bit more cost to the company, no doubt. And you can even go to this net positive impact type of manufacturing, which is good for the company and good for society. So this becomes a win-win type of a solution. So we have done several examples, and I don't have time to get into details, but there are several examples we have done. They're all published. They're there in the open literature. We have looked at this biodiesel facility outside of Cincinnati. We have looked at the design of a house and a yard. This is my graduate student's house when he was, doing his PhD and living in Hilliard, Ohio. So the insight from this techno-ecological synergy is that, basically, if you look at the trade-off between environmental impact and cost, this curve shows the trade-off or the Pareto curve, okay? This is the space of conventional designs that you can have with conventional technological types of solutions. But if you include ecosystems, in your design, you can expand the design space, and this additional green space becomes available to you, which is innovation that you cannot get to by taking a traditional technocentric approach. So these solutions that are techno-ecologically synergistic can be win-win. They can reduce cost or maybe increase cost a little bit, but they can certainly help in terms of resulting in a nature positive future and potentially even people positive by reducing the impact on society. So there are many challenges here. Okay, these are mainly simulation studies that we have done, but these are slowly becoming more popular and getting adapted. by cities and some companies also. But there are challenges. One of the big challenges I want to point out is that engineers, people like me and maybe many of you, we are not adequately ecologically literate. Okay, we need to know more about nature, otherwise we have to collaborate with ecologists, which is what we have done. And also we need, user-friendly tools and applications of these kinds of things. Okay, so, let me now conclude then. The bottom line is that the solutions, that we need are urgent, right? We need to address the challenges of climate change. For that, the net zero greenhouse gas emissions by 2050 is a common goal that is being pursued by nations across the world and by corporations and university campuses also across the world. Ecological degradation is another big problem, and their nature positive decisions is what is being pursued. Social inequities and injustices, people positive decisions is the goal that is being pursued. From the work that we have been doing, it seems to us that if we were to just make small tweaks in the existing system, such as we increase the efficiency, the energy efficiency of our system, or the material efficiency of the system, or we replace conventional energy, fossil energy by renewable energy, or we just reduce the life cycle impact, we don't think that is going to be enough to meet the kind of challenges that we need to meet in this time frame. Okay. If we want to make real progress, what we need is a paradigm shift in engineering. Net zero requires reinvention of industry to become a circular enterprise and not the linear enterprise that it currently is. Okay. Obviously that needs a lot of innovation, a lot of technologies, a lot of policies and so on. But, if we just tweak things here or there, that's not going to be enough. Transformation to a circular enterprise is not a trivial undertaking. Many companies, including some of our collaborators, have already embarked on this journey. Being nature positive requires explicit accounting, for nature and respecting its limits. Engineering, like most other disciplines, as I said, has ignored nature for at least 200 to 300 years. So we need to overcome that paradigm and explicitly understand what ecosystems do as best as we can and account for their role. And, as I tried to show you, through the examples, there are win-win opportunities potentially that we could also, benefit from. And there are, job opportunities potentially and business opportunities that are also there. Several companies are also exploring this space. For all of this, though, we need systematic methods and tools. And that is something that we are working on. So to finish up, I want to just indicate these 3 books that contain some more information. This first book came out some time ago. 2 mechanical engineering collaborators. Professor Tim Gutowski is mechanical engineering at MIT. This is a textbook that came out about 5 years ago on sustainable engineering, and this book came out just in November. That is focusing on this techno-ecological synergy type of idea. And lastly, I want to tell you about this center that I've already mentioned that we are in the process of establishing at Arizona State University. It's the Center for Advancement to a Net Zero Chemicals and Materials Industry, CANZ, CMI for Chemicals and Materials Industry being the current focus. The goal here is to develop the kind of methods, models, tools that I have alluded to in my previous several slides. So that's a sustainable engineering part. We want to connect with molecular science, so actually do experimental work, with other researchers at ASU. Also connect with other aspects of chemical engineering, direct air capture, other approaches that would help to get to net zero. We are also collaborating with the business school, looking at corporate strategy. And of course, economics and policy, have to be there in any effort towards getting to net zero. There are already several efforts that are complementary. At ASU, there is a recently established center by the Department of Energy on electrification of industries, to basically get to net zero. And the second center that was announced just earlier this week is a Southwest Sustainability Innovation Engine, which is a very large center funded by the National Science Foundation that is also going to focus on many of the goals that I have already mentioned. So I want to finish up by acknowledging, a whole bunch of graduate students. I'm not going to read all of their names. The ones with the asterisk have graduated and are working at various places. collaborators at ASU, George Basil and Kevin Dooley, mainly on the business school front. Joseph Excel, who has been a long-time collaborator for almost 25 years. And George Stephanopoulos also at ASU and at MIT. And financial support from various funding agencies. And the last philanthropic foundation, both of them are MIT alumni, just for your information. So let me stop over there, and I'm happy to take any questions and any feedback that you might have. Thank you very much for your attention.
Bhavik, thank you very much. That was enlightening, and thank you for sticking to the time. We have a number of questions from the audience. We also have some questions that were sent in previously, but let me start with some from the current audience. Mining could be making a shift to the sea, to the ocean. Is this worse than land-based mining for biodiversity? It seems like it would be harder to remediate.
So you're talking of things like deep sea mining and nodules and things like
Correct.
that. Right. Yeah, so I had a conversation with someone about that just this morning. I think personally, I'm really worried about that. We really don't understand, the ecosystem that is there, in the deep ocean in particular. And, it is something that is likely to result in unintended harm, something that, as I've mentioned before, we need to avoid. And, historically, a lot of these solutions, in quotes, we have come up with have resulted in unintended harm. So I'm really quite concerned about that. I don't think we should jump into that, without really doing some serious studying and understanding. Before we increase mining, we need to spend more effort on enabling a circular economy. We need to develop technologies that enable reuse of the materials, circularization of the materials that we need. That is where I think the effort really needs to go. Mining, if at all, is going to be a temporary fix. It is not the long-term solution, in my opinion.
Thank you, Bhavik. Here's another question for you. According to Mark Jacobson of Stanford University, the amount of land use will decrease with implementation of wind, water, solar, and storage. His argument is that mining for fossil fuels and nuclear uses more land, including power plants. You seem to disagree with this. Do you have research that counters Mark Jacobson's conclusions?
Yeah, so I mean, I know which work you're talking about, and there are papers that have done this comparison between the land use for conventional energy technologies and these other renewable energy technologies. And I don't necessarily disagree with that conclusion, but that conclusion is at the scale of the technology. Okay, we have also got to think about the other side effects of this. So I'll give you an example. So if we are going to have more renewable energy, we need lithium and cobalt and manganese and copper and so on. So yes, the land area that you need may be less, but what type of land area are we going to go into? We're going to go into the Tongass National Forest in Alaska, potentially. We are already going into the Congo, the rainforest in Congo. Lithium is coming from Chile, Bolivia, these places, have hardly any water. This is coming from the desert. So just looking at the land area is not enough. We have also got to look at the quality of the land. We cannot, compromise on biodiversity because that is something that is already at a breaking point. So I agree, you may need less land area, but that doesn't mean that it's not going to have, the same type or bigger problems.
Fair enough. Now, a question about your discussion of cost. You didn't really compute life cycle cost. I think when you looked at the cost associated with the different technologies, you're looking at trade-offs between circularity and carbon reduction. If you were including externalities, then littering would not be the cheapest because there is a cost to that, correct? Right. So you weren't really doing full cost.
That is correct. In that, and you're exactly right. In that analysis, we just considered the conventional cost.
Correct.
because the reason we did not consider full cost is because the other metrics are accounting for that larger system boundary. And the cost that we considered is more of a conventional, market type of a price.
Agreed. Thank you. Bhavik, what happens to the optimization when you try to factor in the reuse and repairability of products versus just recycling? Have you looked at that?
That's a good question. It's certainly, very relevant. In the grocery bags example that I showed, reuse is an option that we did consider, and that is, better. But most of these bags that we consider are single-use bags. Okay, but so in that example, we didn't consider reuse and things like that in a substantial manner. But in general, refurbishment, reuse are likely to be preferable over recycling. So there is a hierarchy of R's, right? That you may be, many of you may be familiar with, starting with refuse, which is to not use the stuff in the first place. Yes. Right, going all the way down to basically landfill. Refurbishment, remanufacturing, they tend to be higher in that hierarchy as compared to recycling, especially if the recycling is downcycling.
Yeah, as you're aware, there's this Remate Center, which Department of Energy has funded. And actually, you had a grant from them, I believe.
Yes.
And they've been looking at all of these different recycling, refurbishment, remanufacturing pathways and doing a lot of research on those. So it's good that DOE is actually supporting this work. Mm-hmm. Now, I'm going to switch to some questions that were sent in prior to the presentation. Are you familiar with ebb carbon? Is that a carbon dioxide removal breakthrough?
Yeah, so I wasn't familiar with ebb carbon, but I looked them up. And the technology that they're proposing is really interesting. So maybe some of you are not familiar with that either, but my understanding of what they are proposing to do is to take ocean water and electrolyze it. Basically through that, you end up, I'm forgetting the detailed chemistry over here, but essentially, through electrolysis, you're able to reduce the acidity, of the water. And that water then goes back to the ocean, and it has the capacity to take up carbon dioxide from the atmosphere. Right. Okay. So it is potentially, longer term type of CO2 uptake, in the ocean. And also reducing acidity is certainly a good thing. It probably has a place, in the slew of technologies, that are being developed. So I wouldn't say that it's not a viable alternative. The jury is still out. But I think we need to explore all the alternatives or most of the alternatives. And this ebb carbon might be one of the direct air capture technologies, that becomes worth looking at. However, I will say a couple of things. One is that the ocean is a very large system. When you do this at a very small scale, it may look fine. Most technologies at a small scale, you don't see too many negative impacts. The problems arise when you scale it up. So this starts getting done at a very, very large scale. You need electricity for this, and that renewable electricity that they are proposing to use, as I've mentioned previously, there are likely to be material challenges associated, with that. Also the carbonates that they, one has to look at this from a full life cycle point of view, and maybe they have, but if they have, I have not seen, the results of that. So I would say, it sounds very interesting. It looks very innovative, worth exploring. Whether it is the silver bullet or not, there is no silver bullet, to the best of.
Thank you. I was interested to learn that the world's oceans are the largest pool of carbon sequestration, larger than all the plant life in the world. I don't think everyone's aware of that.
Right.
Now, here's there's a few questions about different technologies. Here's another question. What is the best way to incorporate ammonia into the mix of renewable fuels?
Yeah, so ammonia, especially green ammonia, has been getting a fair amount of attention as a chemical battery, for example. So you may have a renewable resource, but, it is intermittent. I told you I had solar panels. I have solar panels on my roof, but I'm still connected to the grid. At a time like this, when it is dark in Phoenix, I need to use electricity from the grid, or I need to have a battery, right? So ammonia could potentially provide a chemical battery, right? That is one of the ways that I am aware of, of ammonia being relevant, in the renewable energy context. I think it's an interesting idea, and there's a lot of work going on, but there are a few things that we need to be careful of. Of course, ammonia, if it leaks, it can, it is sort of toxic. It can result in tearing of ice and so on. That is very well known. But the other issue with ammonia, if it ends up in the atmosphere, is that it can result in disruption or further disruption of the nitrogen cycle. The nitrogen cycle is already very disrupted. Those of you living around the Great Lakes, especially around Lake Erie, are familiar with the harmful algal blooms that happen typically the peak in August, right? Most of the inland lakes across the planet have some problem, with excessive nitrogen and phosphorus. And most of the ocean waters, near coast, the Gulf of Mexico has the largest hypoxic or dead zone in the world. That also appears typically during the summer. So large-scale use of ammonia, this is a potential downside, which is due to the leakage. And that, we should be very careful to avoid, or if not eliminate, leaks. I don't know technologically how possible that is.
More trade-offs, huh? So here's another question. What do you think about the potential of wave energy as part of the commercial power mix?
Yeah, so so again, I think it's worth doing, but one has to really be, do a proper cost-benefit analysis and the environmental impact analysis of that. At a small scale, it should be fine. If we do this at an extremely large scale, the wave energy plays a role in maintaining and building our coastlines. If that energy is now taken up to generate electricity, will it result in beach erosion? And the loss of the property over there on the coast, which many times can be extremely expensive. What kind of effect will it have on the biodiversity in the oceans? So, again, nothing comes for free. It's like the second law of thermodynamics. There is no free lunch, effectively, right? So in my opinion, there is no silver bullet. We are not going to find one solution that's going to solve this problem. It has got to be a combination of solutions, and we will have to constantly be adapting to the realities and the future that we face, and the technologies and other solutions that, will develop over time.
On a broader scale, what do you think about possible solutions to restore the Arctic and cool the planet? For example, people talk about marine cloud brightening, etc.
Yeah, so again, just like deep sea mining, I really worry about these large scale,
geoengineering
kind of approaches. I know technologically we are smart engineers, we can figure it out, and we can, do something like that. But we are also ecologically illiterate, or not very literate. Sorry to be so blunt. Okay. If we are really interested in sustainability, we better have a much better understanding about what nature does for us. And most of us, unfortunately, don't. We never got educated over there. If anything, there is a certain arrogance that, ecosystems, I can handle that. I can engineer them, right? And there are examples of, the Everglades being drained and other places. And in retrospect, those were blunders. And now we are trying to fix them, right? So these very large scale engineering solutions, I'm not saying that they should be abandoned or anything, but I think we need to be very careful, and we have got to pay attention to the ecological impacts of these sorts of things and the unintended harm that could be caused by this, because the unintended harm will be there. That's pretty much a guarantee. That's the second law.
Now, there's a lot of controversy nowadays about carbon capture. Many believe that despite their expense, direct air capture and other carbon capture ventures are valuable and need and are needed to achieve net zero.
Yeah.
What's your opinion? Do you think it's a scalable and feasible approach?
Well, I mean, there is a pilot plant of direct air capture, next to my building. So I've been seeing, what they are doing over there, and the technology, does seem to work. It is expensive, yes, but it does seem to work. I think it has a place, if nothing else works, and if we are not able to reduce our greenhouse gas emissions by other means, this is one of those options of last resort potentially. The people working on direct air capture that I know are saying that this is likely to become much more economically feasible. But right now the estimates are a few $100s per ton, which is too expensive. So again, I think there is a place for it. I think that research is important and worth doing. Maybe there will be a breakthrough that will make that much more economically viable. Of course, the question still remains: if we collect the carbon through direct air capture, what are we going to do with that carbon dioxide? Right? And there is work going on, in that area also, lots of work. But it's not like we just remove the carbon dioxide and we are done. We have to find a way of, doing something with it. Hopefully something better than simply burning it underground.
Bhavik, tell me, what do you think is the importance of the third world usage of forests for firewood as an energy source?
I mean, the usage of firewood as an energy source in the developing world, is potentially, resulting in deforestation and in emissions of carbon dioxide, etc. However, the people who rely on that are the ones who have had close to zero contribution to climate change. These are among the people who are probably the worst off on the planet. So, traditionally, the cultures and the communities that have relied on forests for their livelihood, including, trees and so on, for shelter, for firewood, fuel, etc., they are the ones who have actually valued the forests, and they are the ones who have protected the forests much more than, us others, so to say.
Right.
So I wouldn't, if there are indigenous communities, and it's mostly those kinds of communities that are using, and it is those communities that have a minuscule contribution to this problem of climate change. The problem of climate change is a rich person's problem in a way. It is created by the rich, by the wealthy, right?
This is where,
I think, we need to obviously find better ways, better solutions, for them. I mean, burning firewood and cooking on it is not a very pleasant task. I mean, I've been to villages in India and, even lived in some of them. I grew up in a rural area in India, so I'm quite familiar with that. If they have an alternative, I mean, of course, they will jump at it, so maybe that is what, I mean, I know there is work on smokeless, fireplaces, etc. That is the kind of thing that I think more of that is needed. Their use of firewood, I don't think that's a big problem, honestly.
Well, this is a good example of what you talked about before, about people positive solutions.
Exactly.
We have to consider social equity, and the trade-offs get more complicated.
Exactly.
Is there any credence to the argument made by, by oil and gas companies regarding the need for a hydrogen economy? Unless it's green hydrogen, it may do far more damage than good.
Yes. So, I mean, hydrogen economy, I think, again, it's one of these technological, emerging technologies that is very interesting. It could potentially have benefits. Obviously, it will have to be green hydrogen. I mean, if you get hydrogen from methane, which is sort of the conventional approach, then that's not really helping from the environmental point of view. So I think it does have a place, it is potentially among the solutions. However, there is one thing about hydrogen that doesn't get a lot of attention and doesn't seem to get talked about a lot, which is again got to do with leakage of hydrogen. Hydrogen is not a greenhouse gas. So it is not going to result in, climate change and those kinds of things. But if hydrogen leaks into the atmosphere, what it does is it takes up the oxidizing ability of the atmosphere. It reacts with the OH ions in the atmosphere. It will oxidize, and usually methane that is leaking out, the oxidation of hydrogen will be preferred. So methane will stay in the atmosphere for longer because of hydrogen entering the atmosphere. So even though hydrogen is not a direct greenhouse gas, it will increase the life that methane, which is a potent greenhouse gas, will spend in the atmosphere and contribute to global warming. So again, sorry, everything depends, right? There is no, but that's the world we live in.
Yeah. One of our audience asked whether you can point to a set of references that would discuss possible timelines for transitioning carbon-intensive processes such as concrete, steel, and glass manufacturing to more sustainable technologies.
Yeah, so there are, there have been a few roadmaps that have come out, lately, including roadmaps that are developed, for some of those industries. There is a roadmap that came out for the US to get to net zero. Many countries have these kinds of roadmaps that have been developed. I believe I saw a roadmap recently on the iron and steel industry, to get to net zero. Many times these, and I can't off the top of my head, cite specific references, but, I can, if you want, send me an email and I'll send you some of the references that I'm aware of, some of the work in this area. Many times these roadmaps get developed by experts. Right. So, oftentimes, like what I mentioned is, we need systematic models and methods and software tools to develop these kinds of things. And those, to the best of my knowledge, are not yet available. If they were available, which is what we are, pushing to do, you can develop your own roadmap for the chemicals industry sitting in front of your computer, potentially. That's what we are envisioning will become possible in the near future.
Thank you. We had a couple of questions about large DAC systems. I don't even know what that stands for.
Direct air capture.
Direct air capture? Okay.
Right.
So will large DAC systems be fluidized bed or metal organic framework membranes, etc.?
Yeah, that's a tough one. I don't work directly in that area. The ones that I've been that I'm more familiar with are the metal organic frameworks. That is the one that seems to be emerging. And those MOFs, the metal organic frameworks are, tunable, so to say, meaning you can put specific molecules in them. And they also seem to be more efficient, than, say, the traditional monoethanolamine or other alkaline kinds of, sorbents. But again, that's not an area that I have a lot of expertise in. But I've from the people that I talk to who work in the direct air capture area, they are focusing on zeolites and MOFs and these kind of porous compounds. So that's what they seem to be thinking are the most promising as of now.
Thank you. We're starting to run out of time, but let me ask you one last question. In your mind, what future technologies would you like to see developed over the next 10 years? And how would you invest in society's efforts if you control the purse strings?
So, so what I would say is that, we need to have an effort that makes people more ecologically literate. And we need to develop technologies that are synergistic with nature. I think there is a huge potential over there, and the World Economic Forum report that has come out on it, does get into some of that potential. There isn't a lot of research going on in this area yet, but I think it's a huge opportunity, waiting to become available. So even with the current technologies, if we were to figure out ways of, developing this harmony between technologies and ecological systems, I think, that can go a long way in addressing this net zero, nature positive, people positive, types of goals. At the end of the day, the only system that has sustained itself that we know of for millennia is nature. So I think eco-mimicry, which is what this idea of techno-ecological synergy essentially is attempting to do, circular economy is the same approach. It's trying to mimic, biogeochemical cycles. So I think we need to become, more aware and more familiar with what nature does, the quote unquote technology that nature provides, and then develop, our technologies, to work with that or inspired, by that. There is no dearth of technologies that are being developed. A lot of the chemical recycling methods look really interesting, right? And I think they are, from the plastics point of view, likely to play a very important role. The challenge with plastics, I think, is not, the technology is a challenge, no doubt, but the other big challenge is human behavior. Recycling rates are still abysmal.
At least in the US.
Right. So there we need ways, maybe what is needed is standardization of the materials rather than using so many different types of plastics or so many different types of materials in a product. There should be standardized materials, a few of them that get used, right, by everyone, so that recycling, the end of life becomes a lot easier and actually becomes feasible. Thirdly, the other change that I believe is needed and most likely will happen is decentralization. If we want circular economy kinds of systems, and getting to net zero and so on, we will have to, move away from the very large, localized manufacturing facilities to micro manufacturing and micro recycling kinds of facilities. Again, a lot of technologies of that type are being developed. There is a Walton Solution Center right here, solution service at Arizona State that I was, talking to just this morning. They have done some really interesting work of that type. A lot of cities are also, working in that area. So I think a lot of these types of technologies are, important and likely to play a big role. Those are the areas that I would emphasize if I had, that opportunity. But there is not going to be one single silver bullet out there.
Very quickly, do you also believe that energy production should become more localized and less centralized?
Yeah, I think there is certainly a lot of room for that. Solar is one possibility. And even in Phoenix, I see maybe 5 to 10% of houses with rooftop solar, which is to me quite surprising. I go to India, in the state of Gujarat, 80% of the houses have rooftop solar over there. 80.
By the way, Hawaii, I think, has approaching 50% or something.
Yeah, so yeah, that's right. I've seen those, but yeah, I think decentralized energy is also likely to play a role, especially with, batteries and electric cars potentially acting as storage devices, etc. So for sure, that has also a role, no doubt.
Well, Bhavik, we're running out of time and our audience has pretty much left us. Thank you to everyone who has stayed to the bitter end. I'm going to turn it back over to Douglas.
Well, they haven't all left. There's still 80 some out there. But hey, listen, everybody, thank you very much for attending this event and everything. And particular thank you to Bhavik. Really, you've shown me, I think, a whole new way to think about these issues, and I really appreciate that. And Joseph, you did a masterful job in kicking this off and leading the Q&A and so on, and your own presentation. So thank you both very much for giving this special experience we've had tonight. And I wish you all the best. And for all of you out there in our audience, thank you again for attending. I hope to see you at the next event, or at least you'll see me. And take care. Have a great year.
Okay, thank you.